Okay, class, welcome back to chapter 19. This is the third of the fourth lecture for this chapter. I decided to break up the carbohydrates into two different sections. That way you can digest them in bits at a time. So what we're going to do these next two lecture periods are examine carbohydrates from an organic chemist standpoint. And as I previously mentioned, this will have application if you plan on going on and taking biochemistry. Here's our learning objectives. We've already done that one, protection and deprotection, using them in synthesis, and now these next two lectures we're going to focus on these last three learning objectives. Again, here's our chapter theme. Hebrews 3 verse 4, for every house is built by someone, but God is the builder of everything. Think about carbohydrates as you analyze this verse and the importance of carbohydrates in everyday life. All right, moving on to carbohydrates. So what is a carbohydrate? It's literally the hydrate of a carbon. Carbohydrate, hydrate of a carbon, having a formula of CnH2O to the N. So as many carbons as there are, there's that many H2Os, though it doesn't necessarily contain a water molecule. You may recall that glucose is C6H12O6. So do you see the number of carbons is 6? And the number of H2Os is also 6. And so that's just how the formula is boiled down to. They're important biomolecules, also referred to as saccharides. Saccharides. Or sugars, simply put. So carbohydrates, saccharides, sugars, they're all the same thing. Carbohydrates are chiral, however. And so whenever you consider the chiral carbohydrates, you won't see an R and an S distinction. Instead, what you're going to see is an L and a D distinction right there. And so you don't say R glucose, you say L glucose or D glucose. Most naturally occurring monosaccharides that are chiral, they actually exist as the D isomer. Okay, that's going to be important trivia information. You're going to learn in biochemistry that amino acids tend to exist as the L conformation, or the L isomer, whereas carbohydrates, they are the D isomers when referring to monosaccharides. You may be familiar with many monosaccharides or carbohydrates in general because they tend to end with OSE, so glucose, fructose. You might see sucrose. Sucrose, table sugar, tastes awesome. Glucose is blood sugar. Fructose is typically found in honey. Mannose, ribose. Y'all know ribose from DNA and RNA, deoxyribonucleic acid. It's one of the three components of a nucleotide, the pentose sugar. These will be distinguished as mono, di, or polysaccharides in this class. Aldoses or ketoses, depending on the functional group. Reducing and non-reducing sugars based on how it interacts with Benedict's reagent. Alpha and beta anomers through mutarotation, or hemiacetals or acetals. You already know what those are. And as I mentioned earlier on this slide, carbohydrates' names end with ose, typically, whereas enzymes' names typically end with ase. So when talking about oxidative phosphorylation, you use ATP synthase. That tells me that that's an enzyme. Whenever you ingest a sugar called sucrose, that tells you it's a carbohydrate because it ends with OSE. Chirality in carbohydrates is an important matter of discussion, and I want to spend some time in this slide detailing how to look at chirality in carbohydrates. So what you see here is something called the Fisher projection. We've seen these types of projections in OChem 1, and what you'll notice in a Fisher projection is it's always drawn linear, kind of a skeletal model of a monosaccharide, and this is called the open chain form. Open chain form, okay? And the way these are always going to be drawn is you have an important functional group at the top, and they always end with a CH2OH at the bottom, okay? Now, depending on the identity of this functional group at top, is going to tell you whether it's an aldose or ketose. So be thinking to yourself right now, the ones I just pointed to, are those aldehydes or ketones? Hopefully you came up with aldehydes, and so these are carbohydrates that are going to be called aldoses. Now the next question is, now that you know that those are aldoses, how do you know how many carbons there are? Well, you're in organic chemistry, you know how many carbons there are. So as detailed here, 1, 2, 3, 4, 5, 6. There's 6 carbons, so you might actually call this an aldohexose, hex being 6. Okay, Again, this one, 1, 2, 3, 4, 5, 6, that would also be an aldohexose. This erythrose right here, 1, 2, 3, 4, and so you might call this an aldotetrose. Both of those are going to be aldotetroses, and threose as well is going to be an aldotetrose. So tetrose meaning 4 carbons, 1, 2, 3, 4. Okay, now what this slide's aiming to actually show you, however, is the chirality. And here is a very important thing I'm going to tell you. How do you designate L or D in carbohydrates? What you're going to do is first find the bottom of your Fisher projection, and it always ends with CH2OH. Then you're going to go to the carbon just above it. I'm going to indicate it with blue dots now. The carbon just above it. Now there's a nice little mnemonic device to help you remember this. If the OH on that carbon is on the left, it's going to be L. So notice right here with L-glucose, that OH on this particular carbon, the one right above the CH2OH, aka the last chiral carbon in this chain. If that OH is on the left, notice that it gives the L distinction. Let's look over here at erythrose. Notice that that OH is on the left of the last chiral carbon. Therefore, it's going to have the L distinction. Lastly, right here, notice that it's L, L, left. If that last chiral carbon's OH is on the left, it's going to be designated as L. The opposite is true. If it's not on the left, it's going to be on the right. Therefore, it's going to be D. So if the OH winds up on the right side, it's going to be a D carbohydrate. And all we're talking about is chirality in carbohydrates. So whenever you see L-glucose, what that's saying is that last chiral carbon's OH is on the left-hand side in a Fisher projection. In the cyclic model, there's another way to describe these. We won't talk about that just yet. I don't want you to memorize these structures. Don't know the structure of glucose or erythrose or threose. You don't have to memorize that, but you do need to know how to name these in terms of L-aldohexose or D-aldohexose, tetrose, so on and so forth. 3 is going to be called triose. 4 equals tetrose. 5 equals pentose. 6 equals hexose. You don't really see any other numbers in these carbohydrates. Now, in carbohydrates, let's focus in at L and D glucose. Notice that they are in enantiomers of each other. So let me delete this red line right here. And let's act like this is a mirror. Hopefully you can see that it's the exact mirror image. This OH is on the right. This OH is on the left. This OH is on the left. This OH is on the right. And you can go down the line. And so L and D glucose are in enantiomers of each other. You can see the same thing here with the erythrose sequence or series right here. L and D erythrose, they're just in enantiomers of each other. Diastereomers, recall, are not necessarily defined like enantiomers are. Enantiomers are non-superimposable mirror images. Diastereomers are stereoisomers that are not enantiomers, which pretty much is a fancy way of saying they have one stereocenter changed. Okay, and so notice how L and D erythrose have both stereocenters changed to give you a complete mirror image. But when taking this D erythrose and comparing it to L threose, notice that the top carbons right here, the stereocenter right here is the exact same as this one that I'm circling in threose. However, this one that I'm indicating with the star, this one has changed. Now they're both aldotetroses, but one stereocenter has changed, so that's a diastereomer. And notice in carbohydrate chemistry, when talking about diastereomers, it gets a completely different name. The only difference between erythrose and threose is the changing of one stereocenter, which just means threose and erythrose are just diastereomers of each other. So let's determine if these are L or D. This is pretty easy. They're all going to be the same, as I've been harping in on. CHO is an aldehyde, so think of it like that. So these are all aldoses. You may notice that the last chiral carbon here is designated by that blue dot that I just added. So this is going to be D because it's the OH is not on the left, it's on the right. This is D as well. Sorry. The last chiral carbon is this one. And so the OH is on the right, making it D. Last chiral carbon here, D, so on and so forth. I wasn't very creative with this example, was I, class? That is okay. Now, you may want to practice naming these. So this first one right here is going to be, it's an aldotriose. It's an aldehyde based on that, and it's a triose because it has 3. The second one is an aldotetrose. Aldotetrose, 1, 2, 3, 4, 5. So that's an aldopentose. So on and so forth. So hopefully you can practice those and get good at distinguishing these monosaccharides in the Fischer projection. Okay, you may want to consider drawing the enantiomer of various carbohydrates. So this one, I won't do every example, but just to show you how to do this, I would just write the skeleton out. It has 3 little cross sections, and then just flip every stereocenter. Okay, and that's how you draw the enantiomer of a carbohydrate. Try doing these last 3 examples on your own. And just make sure you take every stereocenter and draw it in the reverse, okay? Identify whether each of the following is an enantiomer or a diastereomer of the following compound. So here's a compound called diarabinose. Hopefully you can see based on the last chiral center of this molecule, the OH is on the right, making it a D carbohydrate. And so let's take a look at this. All these have aldose distinctions because the CHO at the top, okay? And if you notice in, let's call this 1, 2, 3, 4, 5, 6. If you notice in 1, you have this stereocenter's changed, but that one's the same and that one's the same, which makes this a diastereomer. If you look at number 2, notice that's the same, that's the same, that's the same. And so this looks like the same molecule, doesn't it? Okay, all I did is I redrew the same molecule. Okay, if you look at number 3, notice that this stereocenter is different, this one's different, and this one's different. That's your enantiomer because every stereocenter is different. Number 4, different, same, different. This is a diastereomer because it's not the complete mirror image. Number 5, you have different, different, same. That's another form of a diastereomer. And then lastly, in number 6, you have the aldehyde. You have same, same, different. That's a diastereomer. Okay. I already alluded to this plenty of times during the slideshow, so I'm going to go fast through this slide. Aldoses and ketoses. And aldose, there's that glitch again, huh? And aldose are carbohydrates, aldoses are carbohydrates that contain an aldehyde functional group when using the Fischer projection. And a ketoses are carbohydrates that contain a ketone group when using a Fischer projection. Furthermore, the number of carbons can be used to describe a carbohydrate. We've already gone through this earlier in this slideshow. And so D-glucose, I already told you, is an aldohexose. 1, 2, 3, 4, 5, 6. And it's D because the OH on the last chiral carbon is on the right. Okay. Now, over here is some example of ketoses. Notice in a ketose, you have a CH2OH at the bottom and a CH2OH at the top. But right next to the CH2OH is a ketone functional group. So these would be ketoses. So notice aldehydes occur at the end of the chain, or rather the top, but it is on the end. Whereas ketoses have a CH2OH on either end, but a ketone right next to that. Okay, and so let's look at this D-ribulose right here. I would call this a 1, 2, 3, 4, 5. So a ketopentose. Now, is this L or D is the question. You already see by the name that it's D, but right here, The last chiral carbon, the OH is on the right. So this is a D-ketopentose. D-ketopentose. Okay. So let's practice this, describing each of the following using the script L or D, aldo, keto, blank ose. So this is an aldehyde. So we're going to put aldo, and it has 1, 2, 3. And this last chiral carbon has the OH on the right, so that's D. So you'd say D, aldo, triose, 3 carbons. This one you might notice is a keto, because that's a ketone. It has 1, 2, 3, 4, 5. And so we know it's going to be a pentose. And the OH is on the right-hand side, meaning that it's D. So there's your answer. If you look at this one, that's aldo, because it has an aldehyde there at the top. 1, 2, 3, 4, 5, 6. So you know it's hexose. L or D. That last chiral carbon's OH is on the right, so that's going to make it D. And then again we have aldo. 1, 2, 3, 4, 5, 6. So it's an aldo hexose. Last chiral carbon, that OH is on the right, so it's a D-aldohexose. So be practicing those. They are going to show up on your next exam and potentially Friday's quiz. All right, so hang tight. This is a pretty tough slide to unpack. Carbohydrates actually do not exist very often as the open chain models as described by Fisher projections, what we've been talking about during this lecture. Because if you recall, whenever we're making hemiacetals, they tend to stay in the ring form if you can form a 5 or 6 membered hemiacetal ring. And that's what we're going to be showing here. So when this molecule cyclizes, it can use this alcohol and attack that aldehyde. Let me show this aldehyde for what it really looks like. Okay, and if you did that, using that OH there at carbon 4 of this Fisher projection, you would get a 5-membered ring. I can try to show you why it's a 5-membered ring. So it would form a 1, 2, 3, 4, and that O would be part of the ring, 5. And so if that happened, you would form the 5-membered ring, and it can either go to that version or this version where carbon 1, which was your aldehyde, if you look, then becomes a hemiacetal, being a carbon bound to 2 oxygens, one being an ether, the other being a hydroxyl group. However, had I taken another route and used the OH group at carbon 5 and done the same thing, I could have gotten a 6-membered ring. 1, 2, 3, 4, 5, and the O in the ring is 6. Noticing that carbon 1 is still going to form a hemiacetal in your cyclic structure, bound to an ether and an OH, but this time a 6-membered ring. Notice that these are both hemiacetals, therefore they're relatively stable in the cyclic form. These cyclic projections are called Haworth projections, sometimes called Haworth projections. Either is fine, but these are called Haworth projections. So the first one, the open chain, is called a Fisher projection. The cyclic form is called a Haworth projection, and there's more to consider in this one. For instance, notice the 2 different 5-membered rings stemming from attack of the hydroxyl on carbon 4. Notice the difference between those is on your carbon bearing the OH right here, your hemiacetal carbon. Notice the OH sometimes is pointing up and down. We're going to talk about why that is. The same thing happens here in the 6-membered ring, up versus down. This is going to be defined as the anomeric carbon, and pretty much this carbon, which is number 1 in our Fisher projection drawing, it came from the aldehyde. Now let's consider this aldehyde, okay? And let's say you had an OH group come. That's an alcohol, ROH. Let's say it approaches the front. You might get one of those anomers is what I'm calling it, but you might get the OH at the top or bottom. But let's say a very similar thing happened, but this time it approached from the back. You would get the other version. So depending on the direction of the attack, that will tell you if it's the up version or the bottom. You may be confused. Why are we talking about all this? Well, do you remember everything I've built up in this chapter about how to form hemiacetals, it stemmed from mixing an alcohol with an aldehyde or ketone, right? Well, do you see the same thing happening? It's nothing more than a cyclic version of this, an intramolecular version. I just circled the alcohols or hydroxyl groups on your Fischer projection, and they attack an aldehyde, or this happens also with the ketosis, so it could have attacked a ketone. So all what I'm doing is I'm using the same chemistry previously described to show you how these cyclic carbohydrates are formed. It's nothing more than a hemiacetal formation class, and I hope you can see that your hemiacetal that's forming is carbon 1, aka the one where the aldehyde or ketone was. Now that we're dealing with cyclic models, aka Haworth projections, we need to learn new distinctions. So when you form the 5-membered ring in the Haworth projection, we're going to call these furanoses. And so 5 meaning furanose. You may recall a solvent in organic chemistry at this point called THF, which is tetrahydrofuran. And all what that looks like is, it's a 5-membered ring with an O in it. Now, furan, meaning not tetrahydro, but furan, is just the unsaturated version of this with 2 double bonds in there. It is aromatic. You may recall from the benzene chapter. Now let's take a look at glucose. If it were to take this hydroxyl group and cyclize, it would form the 5-membered ring. And so what you would call these is furanoses. Notice that this one's called beta-D-glucofuranose, and this is called alpha-D-glucofuranose. And so furanose means a 5-membered ring because this 5-membered ring literally is a furan ring without the saturation or the unsaturation. So hopefully you can see that with the 5-membered ring bearing an oxygen, it's the same as like a furan ring in a way. And so that's why these are called furanoses. Pyranose is a distinction used to describe the 6-membered version of these cyclic models, the Haworth projection. So we're going to call this pyranose. And that comes from the 6-membered ring right here, pyran. 6-membered ring bearing an oxygen. You may recall this from our protection and deprotection of alcohols, the DHP and THP, tetrahydropyran. Here it shows up again. Remember, that happens if you take this hydroxyl group at carbon 5, react it with the aldehyde to cyclize to give you the 6-membered ring. And looky here, you now have a 6-membered ring bearing an oxygen. And that is a pyran ring. You may notice the same thing right there. Of note, whenever we look at these Haworth projections and you're looking specifically at a pyranose, we're always going to put the OH in the top right corner, whereas the furanoses, we're going to put it at the very top of the pentose or the 5-carbon chain.